quantum mechanics existed because of this experiment. It's a very famous experiment, and it's called the double slit experiment. For many years, scientists knew that if you put light through two slits in a barrier, that you would get this diffraction pattern. What would happen is some of the light would go through this slit, some of the light would go through this slit, and then the light would interfere with each other. The way it interfered is that the distance between here and that point and the distance between here and that point from the two slits had to be some integral number of wavelengths so that the wavelengths got there in phase. And when they did, you'd get some light. And when they didn't, when they got out of phase, you got nothing. You got dark spots in between them. Okay, so this was an experiment, well known, done many times, diffraction grating. And then Einstein came along and studied the light hitting things and knocking out electrons, okay? Yeah, photoelectric effect. He was studying that, and he realized that light looked like a particle. It seemed to always have some integer number of chunks of momentum. It came with little chunks of momentum, just like particles. So he said, light's a particle, and his theory supported that. Well, now that made a big question. Well, if light's a particle, particles we know, they go through slits. They just travel in straight lines unless interacted on by an exterior force, right? Newton told us that. And they would put a little spot of light behind that slit and a little spot of light right behind that spot. That's what a particle would do. So if light's particles, how do we get this? So they decided, let's test this out. They were very clever, found a way to fire one photon at a time at these slits. So they fired a photon. Of course, one photon isn't enough to measure, particularly in those days. So they actually fired thousands, but they only fired them one at a time. So only one photon at a time interacted with these slits. And what do you think they got? Did they get this or this? Well, they got this. They got a diffraction pattern. Now, how was that? You were sending particles in these slits, and you got this diffraction pattern. Well, they didn't understand that very well. So they said, well, let's look and see what's going on at those slits. So these little red things are symbolizing detectors. So they put photon detectors there and said, let's see what's happening at the slit. And when they did, sure enough, they occasionally, when the photon got fired, they'd find that it would go through this slit. And when it did, they'd get a little thing from their detector. And when it did, it'd go straight through, just like Newton said, and stop right at the back behind the slit. And when one went through this slit, it would stop right there, and they got this pattern. So then I was thinking, well, it's the detectors are making the difference. When we detect it, we get this, and we don't detect it, we get this. So whether it was by just luck or whether it's because they were clever, I don't know. But fortunately, one of them decided to leave the detectors on, because if they turned off the detectors entirely, of course, they got this. And the idea was, well, the detectors are interfering. So somebody decided to leave the detectors on, but just not take any data. In other words, the detectors were there detecting, but they just weren't collecting any data. So if it was, let's say, going to a magnetic tape, then there was no magnetic tape loaded. Okay, the head of the tape was still showing what the detector said. The head of the tape was still oscillating because the detectors were working. The detectors were still detecting. Well, what do you think happened? They got this. So they got the diffraction pattern. Okay? So what it turned out was that if they looked, if they collected the data, okay, then they get this. If they didn't collect the data and they weren't looking, they got this. That let them know that it was the actual conscious act of taking the data that made the difference as to whether light was a wave or light was a particle. Well, that was a really big deal. Okay? Suddenly, life wasn't clear anymore. It had been real clear up to that time, and it wasn't clear. Okay, the next one. Here's how that works. A bright young guy named Erwin Schrödinger, German, he was a graduate student, and if you'll notice in physics, most of the big breakthroughs occur with young people because they haven't been in the system long enough to understand what's impossible. So they're still open-minded. They can still think out of the box because they haven't gotten educated enough not to be able to do that. So what he said is, well, look, these things come through here one at a time. The photon obviously can't break up into pieces. A photon's a photon. So it must be going through here, and some of the time it goes up here, which was a smaller spot. Some of the time it goes, each one of those photons must somehow pick a place to go, but it always picks one of these spots and never picks the spaces in between. So what he would do is, he said, well, let's say that this photon is really not a photon at all. It's just probability distribution. Now, by that I don't mean that the photon is somewhere and we just don't know where, and that's the probability of where it is. I mean that the photon doesn't exist as a particle. It's a probability distribution. So, given that it's a probability distribution, some of the probability goes through that hole, some of the probability goes through that hole. In other words, the probability is that some of it could go here. There's a certain amount of probability that goes here. The probability then interferes with itself like a wave, and you get this pattern. Well, when he did that with the math, of course, it worked, and he got the pattern, and the physicists of the day looked at it and shook their heads, and graduate students, I mean, okay, you got the answer, but it doesn't make any sense. Well, then they took his methodology and they applied it to other things of the day, and guess what? It got the right answers there too. And it kept getting right answers. So physicists had to take it seriously, even though it didn't make any sense. Quantum mechanics now is one of the most successful branches of physics ever, and it still doesn't make any sense, you see? To physicists, they still don't understand it, but you're going to understand it by the end of this day. You will understand it, and you'll have that much up on physicists. So that's it. These particles are just probability distributions. Now, here's the way it was. Here's the way that was described. At this point, do we have another one of those slides? Okay. At this point, they realized that it's because they took the measurement, right? Consciousness is involved. They said that the probability wave function collapses to a physical particle when the measurement is made. Okay? The measurement collapses the wave form to a physical particle. So because they made the measurement here, they got a physical particle there. And when you have a physical particle, just like Newton says, it travels in a straight line until it hits something. Here, the measurement was made here. So they didn't have a physical particle until the measurement was made. And when the measurement wave was made here, you got this diffraction pattern, because up until this point, there was no particle. It was just probability. You see? So that was the answer. That's still the answer. All right? Now, I'll give you a couple of quotes from some of the, we'll go one more slide there, to people who helped develop quantum mechanics. First is from Eugene Wigner, and he was a Nobel Prize winner. He was one of the leading scientists that worked on the original quantum mechanics. He says, "It will remain remarkable in whatever way our future concepts may develop that the very study of the external world led to the scientific conclusion that the content of the consciousness is the ultimate universal reality." Again, these are not New Agers, right? New Age hadn't happened yet. This is back in the early 1900s, 1950, 1920, 1925, that kind of time span. These are top-notch physicists. Max Planck, often known as the father of quantum mechanics. He didn't invent it, but he did a lot of work in it. And science cannot solve the ultimate mystery of nature because in the last analysis, we ourselves are part of the mystery we're trying to solve. And that sounds just like Einstein. The last quote, it said, "The space of physics is a function of our conceptual scheme." In other words, what's out here, our reality, is entangled with what's in here. Okay? So the summary of that is, 1, reality is a product of consciousness. 2, reality, mass, particles exist only as probability until a measurement is made. 2 fundamental truths that we knew back in the early 1900s. Now, we don't even seem to know that now, right? Science would probably read those 2 things and say, nah, that's not possible. Well, what happened? How come we kind of dumbed down over the last 100 years? Well, it's because, like in any field, when you hit the wall where you just can't take the next step, just like Einstein did, I have no idea, what elementary concepts to use next. Well, you avoid it because that's a career breaker, not a career builder. You go work where you can make something happen, where you can, write papers and get funding. So this whole concept was just kind of walked away from because nobody knew what to do with it. It was a dead end.